Okay, so let's start again. So the next, we are staying in Austria, but with a German speaker. So Mario Ullrich for Johannes Kepler University in Linz. We'll talk about the power of adaptation and randomization.
So thank you very much. Thanks for the organizers for giving me the opportunity to speak here. It's kind of an honor to be allowed to be a speaker, and they take it as a compliment that I'm chosen to be one of the speakers after the conference dinner and be recorded here. It must be proof that I'm professional. So let me speak about the things I'm doing here. So it will be a bit general. I try to, if there are any questions, I give the talk for the first time. I will draw the pictures for the first time, so please be calm with me with that. But I'll try to introduce everything that we need here. So what is the general framework? It's only the first slide. So what is the general definitions I'm trying to use here? What is the pointer here? Okay, so for me, as coming from more an information-based complexity point of view, doing complexity theory, I somehow need to formalize everything, and then I look what is the best I can do, right? And for me, what a computational problem is I have a set of inputs. This is kind of the things that I put into my computer, which are a subset of some normed space. You might think of F just being the unit ball, which is typical in our community here, but most of my talk will not be about the case that F is the unit ball of a space. It could be more general. I have a normed space Y, which is just to specifying the error measure, because if I want to approximate something, I need to tell in which norm I'm doing it, uniform norm, LP norm, whatever. F could be thought be the unit ball of a Sobolev space, or I will draw a picture in a second. I have something that I call the solution operator, which is only a formal object. You never need that. Maybe you do not have access to any values of it. It's just to specify S is what I try to do. X is kind of the input, Y is kind of the output. So let me draw a picture which suits this more, is a little bit going into the direction of geometry, which means my input might be some vector in some, you could always think on this example. I have an L1 ball. Think of an L1 ball in very high dimensions. Or think of a Sobolev space if you want to, but we still draw it as something like this, right? And now I want to approximate the objects in this, that's not a good L1 ball, but yeah. I'm not here because of my drawing skills, I guess. So if you want to approximate every element in this guy X, but what do I mean by approximate? I somehow need to say what the measure of my error is, right? And let's think the error I want to use is L infinity one. Okay? Again, L infinity n. So I get some vector x, which is just a vector. And now I want to get an approximation, which is then in this L infinity, and I want that they are close, right? So depicted just as a picture, it is I have my L1 ball here, I have my L infinity ball here, and since I only want to approximate X itself, the mapping S would just be the identity. Okay? So the picture you could have in mind is, there is the mapping S, just mapping the L1 ball to the L1 norm itself, right? It could just be S of X equals X. Often I use now the notation F, but yeah, you know what it is. Okay, so this is the mapping S here. So that's just kind of formal. So what has all this to do with algorithms? That's just an operator, that's just a picture, right? So what we want to do is we want to approximate things. And to approximate things, you have data. And we need to formalize this, right? So what can I do? I'm only allowed to compute X. Maybe my picture was not complete. So I map X to my X here. And I very much hope that my approximate solution is somewhere in this small L infinity ball here. Okay. We only have data, what I just said. So what we can do, when we saw it in many talks, is I can compute some functionals. I can compute some information, so I'm somehow mapping in a way, I will explain in a second. Maybe we just get some numbers, call it L1 of X up to Ln of X. In my talk, small n will also always be the number of data. Okay? And once I collected this data, I'm going back to my approximation. Okay, that's just the general concept of an algorithm. I don't say anything about computability or whatever. It's just an information complexity point of view. And that's the last point here about we usually have to fix some class of admissible information. Okay, so something like we have function values or values of some transform, Fourier coefficients, derivatives, whatever you want. You can formalize this and then you can study what is the best you could do. In this talk, most of the talk, for me, the admissible information are arbitrary linear functionals. I understand that's a theoretical thing, but the questions we were answering here, there are many open questions, clearly. Okay, so in the rest, most of the talk, I'm allowed to compute arbitrary information. Okay, so these functionals can be anything. Anything that is bounded on the space of L1. I said n here, which is actually everything. Okay, so the goal is to compute S of f. So this, I should stay with f. Sorry for that. F and S of f. For all f in the class f, using only information from this class of functions. And to see the example here, right? S could just be the identity S of f equal f. So this writing S maps from x to y is nothing but saying two things. First of all, x is embedded in y because S must be a bounded mapping. And second, I'm specifying the input and the output. Again, it's just a formal way of writing down my problem. And this then means that I want to approximate an element f of x in the norm of y. Yeah, there is no f.
You just take this element as an element of other Banach space. It's not approximation.
Not yet. And the next slide will be the approximation. Sorry if I said something wrong.
S of f?
No, then the problem, you're right. The problem is then the approximation in things. Of course, this is only an operator. And just to get at the set f, because this is kind of maybe the unit ball of x, we might now just consider even something that's more terrible, whatever. If this is a terrible set for you, it's a non-symmetric set, which is off. Okay, so as I just said, that's what we are going to do. We compute some functionals, or we have some functionals, and we may use an arbitrary reconstruction mapping, which we call phi, that does nothing but taking these n numbers and recombining them in some way to get an element of the output space. And this is what I would call an algorithm. Okay? So this phi might be linear, non-linear, whatever, continuous, non-continuous. And the information that is here might be adaptively chosen, randomly chosen, whatever. There are many different concepts. And of course, if I say I'm talking about algorithms, I need to specify what setting I'm in. And the question I'm asking here is, so I do not care much about the reconstruction mapping here, it's a different story. I just asked the question, how much can be gained if the functionals are chosen adaptively or randomly, right? So I could fix my measurements from the beginning. Maybe I have a physical device, I cannot change it, it's just a given. Every functional is kind of a measurement, I just cannot change it. This might be a valid point, but many people in this communities also speak about adaptive algorithms and especially randomized algorithms, right? Which at the end is, I chose these functionals randomly. And I think it's a very natural question to ask how much can be gained by that. Okay? What is the maximum? Because it's obviously you take a more powerful class of algorithms. So you do that because you hope you gain something. And now the question is, how much can be gained? Okay, so make this precise. What do I mean by an adaptive algorithm? And I know one could discuss if this is the only concept of that. It's most likely not, but I have to specify my setting. So the most general form of an adaptive mapping is, for me, the following. I call it N is this, so put it here. This is the reconstruction, phi, I do not care about that here. And that's kind of the information mapping. So I choose my information mapping in the following way. That's the most general thing in this talk here for deterministic algorithms. I compute the first functional, L1. I look at the value I get, and then I decide what is the next measurement I'm doing. I look at the number, I look for the next measurement, and so on and so forth. So I recursively define my information. This is what I call adaptive. So this NN is given as this recursive formula, and yes, every linear functional here might depend on the first n minus 1. Okay? I call this an adaptive choice of information, and I denote the class by this an with a det. This det means these are all algorithms taking inputs in f, outputs in y, are deterministic and possibly adaptive, and using n informations. That's just a class, all class of information you might imagine in this class. If I now know that I do not use this recursive one, actually I fix n of these mappings in the beginning, so I tell you in advance what are the measurements, it's my measurement device maybe, I cannot change that in the meantime, then I call this non-adaptive. And once you are in a non-adaptive setting, you are very close to classical approximation theory, to things from geometry of Banach spaces and stuff. That's the typical thing, and you will see that these relations are quite precise in this context. And now the question is, are we able to connect the general theory of optimal algorithms, information-based complexity, to the classical theory of approximation and geometry of Banach spaces? And I think we succeeded in a quite satisfying way. So so this is a non-adaptive choice of information, and all algorithms that only use non-adaptive choice information are denoted by a and that with a non. So I already have two classes of information. Maybe I make a picture of that. So we have this a and that, and the smallest class we can imagine, too small for that, is a and that. So okay, so this is clearly a smaller class of algorithms than this one. Okay, let's go to randomized algorithms. What is a randomized algorithm? Again, we might discuss if this is a nice concept or not. It's just I propose something, right? But I think that's a well-accepted concept. Randomized algorithms are just random variables where each realization is a deterministic algorithm. I think it's a natural thing. So formally, this is a mapping of omega and f to y, which is specified by a whole family of deterministic algorithms. And you have this probability space here. Okay. So again, I use a and run this time, is the class of all such algorithms which are possibly adaptive. So each realization, yeah, sorry?
Does this include, say, quasi-Monte Carlo algorithms? Or does it have to be a good approximation to a probability distribution, or do you just not care?
No, I don't care. It's a very general, yes, of course, quasi-Monte Carlo is a very good thing in that. You might think, so for example, what is a good, not a good adaptive algorithm? The bisection method. Everyone knows the bisection method, that's adaptive. Cubature formula is usually non-adaptive. Randomized, you could take, there are many choices. What is a good adaptive randomized algorithm? Randomized bisection maybe, I don't know, but I do not, all these algorithms are in this class, okay? I do not say something if these algorithms are good or not, it's just a class of algorithms. Okay? So I have this, a run here, which is the class of all possibly adaptive algorithms, and a run non is the class of randomized algorithms where each realization is non-adaptive. Okay? So these are our classes. So to complete this picture, we have the randomized non-adaptive algorithms are clearly a larger class than the deterministic non-adaptive algorithm. That's not so clear. By the way, there is some problem with measurability, which made it a bit complicated. Look to the paper if you're interested in this, but that's not a serious problem, okay? So the class of randomized non-adaptive algorithms, the reason for that is if you take a random variable, which is just a point mass, then you get a deterministic algorithm somehow. That's the idea, but that's not completely true in some sense. So you have the randomized non-adaptive algorithms, which are a larger class, and then you have the largest class you might imagine. So I'm allowed to compute everything at random, everything random and adaptive and everything. That's the largest class of algorithms you might imagine. That's the smallest class we usually consider. Of course, you can restrict these algorithms to be linear and things. I do not talk about that here for large parts of my talk. Clearly, I need to say what is the error of an algorithm, and since I consider two types of algorithms, deterministic and random, there must be different choices of a measure somehow, right? So for a deterministic algorithm, no matter if adaptive or not, I consider the worst case error, that's typical, so I want to approximate S of f by an algorithm in the norm of y, and I'm taking the supremum over my input class. Classical. And now if I take a randomized algorithm, I just put an expectation here. And why do I just put an expectation and not the mean square error or whatever? Because that is the weakest error criterion you might imagine. It's really the weakest one. So if I now do something like the mean square error, that's an even more harder error, right? And you will see our results. So our results are the strongest for this, right? You can also think about the pth mean of the error and everything. All results will be true of this talk.
Mario, why don't you take expectation of the supra?
Because that's not a randomized algorithm anymore. Because then you take an expectation, right? You take a random element, and then you want this algorithm to be good for all f, which is then no longer randomized. I get it, but this no. No, you take this. If you take the expectation of the supremum, that's a method for finding, by the probabilistic method, a good deterministic method. But it has nothing to do with randomized algorithms anymore. The power of randomization is that you can use basically the averaging for every f. What you say is very interesting, and you know I'm working on that, but this is not an error of a specific type of algorithm. That's what you ask is more about the power. Is it possible to draw random data and then get a good worst case algorithm which is deterministic? That's your question about it. But I could formalize this later if let me try to be in time here. Okay. Yeah, we may omit the y or the x or whatever norm it is because it's clear which norm you are taking by the element that is written in it. Yeah?
You should have some dependence on the measure there.
What measure?
Because you define the randomized algorithm
probability
depending on the measure.
The probability measure is fixed. Fix some probability measure here. So I did not get the question here. Why should I do that?
Well, you are doing it.
Yeah, because it depends. This number depends on this probability measure.
No.
The probability measure is given together with the algorithm. And here's the algorithm. So the algorithm, I don't get the question. Because if what you are saying were right, then I need to also take, I don't know, maybe it's just...
No, the randomization depends on the measure.
Yes, and I will take on the next slide the infimum over all algorithms.
You fix the...
No, I don't fix anything. No.
Oh, you don't fix the
No.
measure. You say any measure.
Yes.
Okay, thank you.
It's like the expectation. So that's like if you take a random variable, then the probability space that is somewhere underlying probability, no one cares about this probability space, right? You only care about the distribution of your random variable and not the omega stuff, which is hidden kind of. Okay, so I do not say that I will come to that. Okay, so what I'm doing now is I consider the nth minimal errors for all these classes. Okay, so you instead of considering the error of one specific algorithm, I take the infimum over all possible algorithms from a class. And the class could be the deterministic non-adaptive, randomized non-adaptive. Okay, so there are four numbers. So once I fix my problem S and my input class F and my number of possible informations N, once I do that, I only have 4 numbers, so to say. And I want to know how different are these numbers, right? And as it can seen by examples, there are many examples, but I don't have time to talk about that, is that these minimal errors in the different settings can be quite different. But how much? And the question that is not just for you to think a little bit about, do you think there is any reason that these things are related, right? It's not so obvious that, especially if you do randomization, why should a problem that is solvable in a randomized setting be solvable by any means by a deterministic algorithm, adaptive or not? I don't know. Why should this be possible, right? And we will see that it is. So for the rest of the talk, I assume S is a linear and bounded mapping. Might be different for nonlinear mappings. But as I told you, I mostly think about the identity, and this is the approximation problem. Okay, so here are some previous results, which show that the whole problem is old, and there was some progress already many years ago. So already Bachwalow in 71 noticed that if the input class F is a convex and symmetric set, you might think of a unit ball in the Banach space. If you want, you can think all the time of the unit ball. And if this is convex and symmetric, then adaptation does not help. So Gall and Micheli, I think, were the first who proved that in the generality here. So the error of non-adaptive deterministic algorithms is always upper bounded by 2 times the minimal error of a deterministic one. What does it mean? If I have any adaptive algorithm in a class of convex, which the class is convex and symmetric, that's the only assumption I need. If I have any adaptive algorithm in this setting, I can just write down a non-adaptive one, and this non-adaptive one has an error at most twice the size of the adaptive algorithm. Right? That's kind of magic already, but it's well known for many years, right? So a different thing that was known is if you have Hilbert spaces on both sides, for example, you make approximation in a Sobolev space in L2 norm, a Sobolev-Hilbert space in L2 norm, both sides are a Hilbert space, then you know even more. You know that not only that adaption does not help, also randomization, in addition, randomization does not help at all, right? So all these classes, the power of all these classes basically collapses. They are all the same power. You do not need randomization, you do not need adaption. You can just use the easiest class of non-adaptive deterministic algorithms. And why is it interesting? Non-adaptive deterministic algorithms usually give rise to an a priori guaranteed error bound. And all the others do not, right? Randomized algorithms do not really, because it's random, you only get something with high probability. And for adaptive algorithms, you usually have no idea what your computer program is doing, right? How can you tell anyone that this will be good if you do not know what the algorithm is doing, right? The algorithm decides on its own what it's doing, so yeah. Okay, so this is also already known by Erich Nowak from '92 that this holds for Hilbert spaces. And if you now go to the general situation, right? And general means not only general Banach spaces, but also removing the symmetric condition, just taking convex sets. You might think of approximation of monotone functions, for example, or positive functions, right? Just all your functions in your class are just non-negative. Then this class is not symmetric, obviously. Okay, in this case, it was known that, again, in a deterministic setting, non-adaptive deterministic algorithms have an error that is bounded by something like n squared, like the adaptive one. So you lose at most a factor n squared if you have n data, where if you go from an adaptive to non-adaptive algorithms in a deterministic setting. And a big question, at least in our field, was for a while, what about randomized algorithms, right? If you now ask exactly the same question, you have a convex and symmetric set, then you know that adaption does not help for deterministic algorithms. There is no reason to use adaptive algorithm in a deterministic setting if your input class is convex and symmetric. At least if you haven't the feeling that you already have the optimal algorithm at hand, right? Clearly, if we don't talk about optimal algorithms, then of course the best known adaptive algorithm might be better than the best known non-adaptive one. Okay. Yes, and it was open for quite some time if the same holds for randomized algorithms. And this was very recently solved by Stefan Heinrich in a series of impressive papers. And he was basically considering random methods for parametric integration, which means you integrate a function, but there is a parameter inside. And now you want an algorithm that gives you an output that is good for all these parameters. I think it's a natural problem, never studied before. And he proved that in the randomized setting, adaption might help. And let me now give a theorem that was proven subsequently by Robert Kunsch, Erich Nowak, and Marcin Pnuk, who's also in the room, I guess, and some improvement a little bit later, is that if you consider such a simple problem that I just depicted on the blackboard here, already there you get a big gap, right? Take the L1, say inputs of L1, make the error in L infinity with a very, very big M, then you can already get that the error of randomized non-adaptive algorithm is strictly lower bounded by say something a factor n as the error of adaptive algorithm. And maybe one needs to get used. Every inequality of this type is basically can be understood in two ways. It could be understood as a lower bound on the error of non-adaptive algorithms, but the same way you could say this is an upper bound of the form 1 over n, no, this is the one, yes, it's like this, 1 over s1. Which means it's a way around. If you know that there is a randomized non-adaptive algorithm, right? A randomized non-adaptive algorithm with some error, then there might be an adaptive algorithm which is better by the order 1 over n. Okay? It's exactly the same statement, but just phrased in the way around. Okay, so this by this picture here, as I explained to you, the class of randomized non-adaptive algorithm is clearly bigger than the class of deterministic non-adaptive algorithms, which means this lower bound here also implies the one for the deterministic. So we know there is a problem, an easy problem by the way, almost easy to write down, the proof is not easy, that the difference between randomized adaptive algorithms and deterministic, non-adaptive or not, in this case that's the same, and deterministic algorithm, the error is really of the order n. There is one problem, right? Is it sharp? Any reason to believe that's sharp? Maybe not, but it is. And the main result we were proving, now we spent quite some time on this paper, and there are a lot of results. We collected all that was known for a while, so it's almost a survey paper, but it's worth to look at, I guess, is the following. I will give you an easier form on the next slide, if it's not easy to see directly. So if you have some Banach spaces, an arbitrary linear mapping, then for every convex f, you do not need symmetry, you get that the error of deterministic non-adaptive algorithms is always upper bounded by this kind of geometric mean of the errors of randomized algorithms. Okay? You have this kind of geometric mean here, and some factor n to the 3/2 in front. And yeah, maybe I haven't said, for us it's important that instead of using n informations in the randomized case, we replace that by 2n information in the deterministic case. So you see, I see this 2n here. And this is also necessary. We know that's necessary in some cases, not always, that's matter of fact. But in this generality, I I do not really care if I take n or 2n function values, or informations. There are a lot of improvements. So if f is symmetric, so the first case just means assume f is a unit ball of a Banach space. Then you can replace the n 3/2 by n. And by the example on the last slide, this is sharp. Okay, you cannot do better. We really know now, to some extent, that up to an order n, up to this factor n, so we know the maximal gap. I come to that in a second. If one of these classes is a Hilbert space, so if you make, say, L2 approximation, you can also write n. If f is symmetric and you make L2 approximation, you can even replace it by square root of n. And if the input class x is a Hilbert space and f is its unit ball, no matter what kind of approximation you are doing, you can also replace n to the 3/2 by n over square root of n. This is hard to digest, so let me make it a little bit easier. For some people are used to rephrasing this in terms of Karl's inequality. Right? Karl's inequality is known, many people use that to compare entropy numbers and things, and this is a formulation of this flavor. So if you take a convex f and so on, it's the same assumptions here. Then the error of deterministic non-adaptive algorithms are bounded by n to the minus alpha plus 3/2, as long as the error of randomized algorithms decays of order alpha. Okay? So this really means as long as these numbers decay somehow regularly, like n to the minus s or n to the minus alpha, you get the same decay for this much smaller class of algorithms by adding some 3/2 in the general case. If the class is convex and symmetric, like a general unit ball, you just lose the factor n here. And again, there are more improvements possible if if x or y is a Hilbert space. Time flies, so let me take to the table, which somehow shows what we know now. That's the state of the art. This means what is the maximal gain in the rate of convergence you might get if you go from one class of algorithms to another. You will see this table again at the very end, by the way. Okay, so if I go from deterministic non-adaptive algorithm to deterministic algorithms, I showed you there's no gain at all if f is convex and symmetric. But if f is only convex, we only know the gain must be between 1/2 and 3/2. If you go from deterministic algorithms to non-adaptive to randomized non-adaptive algorithm, the gain is between 1/2 and 1 here, 1/2 and 3/2 here, and same here, right? If you go, that's the most general column here. If you go from arbitrary deterministic to arbitrary randomized algorithms, we now know you can gain maximally the order 1, and this is also sharp. And the same here. If you use adaption in the randomized setting, that's 1. And all the other intervals here, these are the open problems where at the moment we don't know. And by the way, all these upper bounds that are given here, except this, are proven in our paper. Okay? It was not clear so far of this. And the lower bounds are always given by examples. Okay, like the example L1 to L infinity. Okay, so what has all this to do with width? 10 minutes. Let's hope. The most important tools we were using is actually widths of convex sets, which is a kind of concurring concept as numbers of operators. Right? So it's almost the same concept, but it's just different. You ask this, so the S numbers of operators in the sense of Peach are measured somehow to measure the compactness of an operator, while the n widths of sets are somehow related to size of sets. And what we did is we did a common generalization and then proved several results that are close to S numbers and widths and so on. So for example, the Gelfand numbers of an operator S in some set F are given by this. So what is it? I take n linear functionals, the best ones, and now I take the supremum over all two elements of my class F that I cannot distinguish by my data. Okay? So I collected n data points, and these are all F and G are now all these guys that produce the same data. And I'm just looking kind of the radius of the set. So it's 1/2 the diameter here, right? So I'm just looking, once I have my data, there must be elements I cannot distinguish. And since I cannot distinguish them, this is a clear lower bound for algorithms. It's a kind of. But I will show you, make this precise in a second. Yeah, it's really a generalization, these concepts. So if S is just the identity mapping, then you come back to the Gelfand width, which is well known in approximation theory. And if F is just the unit ball of the Banach space X, then these are the Gelfand numbers in the sense of Peach. Two more widths, I'm sorry, but these are important here, but maybe some of you already know at least the first of them, the first of these two. So the Bernstein numbers of an operator are given by this formula. Let me save time by just reading this. It's the largest n+1 dimensional ball in the class F with respect to this norm. It somehow also represents a ball inside, I don't draw this now, this can only be ugly. Okay? It somehow gives you the largest n+1 dimensional ball in F with respect to a slightly different norm. Again, if S is the identity, that's just a ball inside of the set X. And the second one, which are the Hilbert numbers, they are almost not known in the community, I guess, but they are a very powerful result. The Hilbert numbers look strange, right? So you have some mapping A and C, some additional mappings which map the set X, Y to L2 and L2 to X and so on. And they could be understood as the Gelfand numbers of the most difficult Hilbertian subproblem. Okay? So you are looking for the biggest Hilbert space that fits in your class F, and you look on the right-hand side for the, say, strongest Hilbert norm that is still larger than the one you are originally considering. So this is kind of the Gelfand numbers of the most difficult Hilbertian subproblem. That's what you might think. If you're interested in details, please check the paper. And what was the motivation for us, so because we found this kind of result, is that if you only consider unit balls, then it is known for a long time due to Peach the following theorem. But let me phrase this. So first of all, it is known that these numbers are related. Hilbert numbers are the smallest, Bernstein numbers are in between, and the Gelfand numbers are kind of the largest in the context we are considering them. There are also something like approximation numbers, Kolmogorov numbers, and so on. There are many different numbers. Peach invented many of them, or at least studied them in an axiomatic way. Sorry for small. But, and this is clear, and the following reverse inequality has been proven by Peach already in the 80s. And it went totally unnoticed in our community. And why this is important for our community, I'm not sure if I will have time. There will be some add-ons. Simon suggested that I give you some hints for questions. Okay, so this is the theorem of Peach from the 1980s, which we found some time ago, and this was essentially known to him, and I just made a small note out of it and improved the constant a little bit. Okay, so you can, can be shown is for all linear mappings, you get that the Gelfand numbers, really in a convex and symmetric setting, are bounded by n times this geometric mean. And the proof is very nice, very nice. I like it very much. Not mine, the one of Peach. Okay, and what we did in our paper, we extended that, so they extended the unit ball to general F, and for this we required an additional square root of n and some constant. Okay, that's already the heart of our proof. You might see from our main theorem this was already close. What is missing? It's still missing that we connect these width and S numbers to algorithms, right? And the first result is well known, and it's classical. I was not even looking for a reference. There are many books in that. You can find it. Yes, okay. So first of all, the Gelfand numbers are basically the same like the minimal errors for deterministic non-adaptive algorithms. That's what I told you in the beginning. It's kind of almost obvious to see, right? That if you have an S and a subset F and some N here, then the Gelfand numbers are an upper and a lower bound up to a factor of 2 for the minimal errors of all deterministic non-adaptive algorithms. Okay, so the Gelfand numbers are clearly important here, but only for the most simple case. And which was not so obvious for a while. There were some preliminary results of Stefan Heinrich, but they were not so powerful as they are. But this was proven by Robert Kunsch in 2017. I think it was maybe, yeah, whatever, 2017, is that the Bernstein numbers, which could be much smaller, that the Bernstein numbers are indeed a lower bound for the error of the best randomized adaptive algorithm. Okay? So once you know the Bernstein numbers, you have that's an ultimate benchmark. That's an ultimate lower bound for everything that I presented to be an algorithm. You might have a different concept. Please let me know if you have a concept of algorithm that differs from mine substantially. Okay, so this is the lower bound here, and now you have seen our proof. Okay? You see that I can relate the Gelfand numbers with the Hilbert numbers. The Hilbert numbers are smaller than the Bernstein numbers, which means this result is also true with the Bernstein numbers on the right-hand side. And now you have these relations to algorithms. Done. That's the proof. And now I have 4 minutes and 3 add-ons, so let's see how far we can go. So this result, so you already have seen our proof. I talked about algorithms. But you might already guess that by these results on S numbers and so on, many of you were working with Kolmogorov numbers and related concepts, you might already feel that there must be something more to do, and it is. So let me start with with 3 add-ons I give you, which are not really related to IBC. They are not closely related to the theory of optimal algorithms, but still might be interesting facts. The first one, so the Kolmogorov numbers is just the error of best approximation on an optimal subspace. Okay? You take the optimal subspace, and then you take the best approximation for every element f. Okay? So in general, there is no direct relation to algorithms. It's a benchmark for optimal approximation in classical approximation theory. No one claims that the best approximation here can ever be given by any algorithm. And I can tell you, in general, it's not. There are a lot of examples where we just know that the Gelfand numbers are just much larger than the Kolmogorov numbers, which means you cannot achieve best approximation, right? You can only do something weaker if you think about algorithms. So in general, the Kolmogorov numbers are not a good benchmark, I guess, for algorithms, I would say. Okay, the theorem, which was already proven by Peach, I do not need to put my name here. It was really written, but only in a footnote on page 47 in 1 line, is that if you consider a symmetric, convex and symmetric, he only used unit balls, but okay. So if you take convex and symmetric sets, and you already know that the Bernstein numbers have some kind of regular decay, then the Kolmogorov numbers are upper bounded by n times the Bernstein numbers. And this, I show you this result because for anyone in approximation theory, you might know Mityagin and Henkin, which are basically the kind of godfathers of width. And there is a lot of results, and they had a big open problem, which was open actually, until, not even Peach knew that this was known. I asked Peach himself before he died recently, and he did not know. So it was kind of, went totally unnoticed for many years. Many of you know the book of Pinkush from '85. Pinkush did not know. He posed the problem of Mityagin and Henkin and said this is still open and one of the most important problems in the field, but it was already solved when he posed the problem. That's one. Another one, which has attracted a lot of attention recently, and we also want to work on that a bit, but it does not fit the theory here. You might have noticed I only considered linear functionals as information. And why linear? Is it good to take linear or not? I don't know. So what has recently been done by many people also in the room, and I think Ron DeVore and Albert Cohen and so were guys who really started this kind of study, is the manifold width could be understood as kind of nonlinear width. So instead of taking linear information mappings, you just take continuous mappings, okay? You're allowed to take arbitrary continuous information, like the phase of something. It could be the absolute value of a linear information could be just continuous, but this is a stupid example. But you might think of arbitrary, say, continuous parameterizations of a manifold, and this is then the kind of the parameterization you're using, right? And it's well known, again, it's well known that the manifold widths are just lower bounded by the Bernstein numbers. This was proven already by DeVore in the 90s and others, right? And by all our comparison theorems, we can just say that these manifold widths cannot be much smaller. So this concept cannot be much better than the concept of non-adaptive deterministic algorithms. And with much better, I mean, again, the factor 3/2, or smaller, smaller concepts under assumptions. And I skipped the last add-on, and wait, that was too fast. Let's just say some words about open questions. So both for the visual n without geometric mean is the thing. And you saw the picture. There are a lot of things that are not known. What is the maximal gain? We do not know any S number for the error of randomized non-adaptive algorithms. We only know it exists. We know we can find an S number, but we do not know how to write that geometrically. Yeah, restricted classes of information, adaptive choice for continuous information is the thing. And what about nonlinear S? We do not know, but that's open to discussion. So thank you very much.
Questions, comments? Yeah.
Just very brief comment. I think that this direction is very interesting and very important. Because now there are a lot of asymptotic characteristics of function classes. And to have general relationships between them. This is just particular case based on algorithms, but there are many others. I think it's very interesting, and no one did this systematically, I guess. There are some wonderful results like causal inequality and others, but it's not done, I would say, in a systematic way. Probably it makes sense to do.
So we were thinking about some kind of axiomatic characterization of width. You have it for S numbers. You know what an S number is. Peach invented that. You have some axiomatic properties. You can check that done. For width, that's not so easy. What do you mean by a width of a set? Yeah, for me, it's not clear how to characterize if something is related as a width, allowed as a width or not. It's kind of a thing. Because if you have this axiomatic thing, and this was the stuff here, you can then characterize what is the smallest width and what is the largest width in our universe. And if you have this, then you can prove bounds, right? But for this, you need correct definitions.
Yeah,
That we all agree on, that are good definitions, right? That's the main problem. You can write down any definition, but...
Are there other questions? Yes.
If your input set is a unit ball of a Banach space, do you have any kind of conjecture what can you gain by going from that none to round none?
I don't know. And that's a very good, I like this question. Thanks, Martin. Were you instructed by me or someone else? I don't know. So this is this gap, right? That's the only gap we have for convex and symmetric sets. We do not know just the classical setting. You have a unit ball of a Banach space, you make approximation in the unit ball, in some other Banach space, right? What is the maximal thing you could gain by just randomization? You don't talk about my strange concept of adaption. You do not need to know and like my concept of adaption, but just taking from non-adaptive deterministic to non-adaptive random. And actually, I would be very surprised if this is also not known for 30 years, but we just do not know, right? So what is the best? What is the problem? And why do I don't believe that this is 1/2? So we do not agree about the conjecture maybe. If this is 1/2, right, you gain the order 1/2 already for integration, right? There are classes where you cannot integrate deterministically, but with a normal Monte Carlo method, you get the order 1 over square root of n, right? So you gain the order 1/2 for the easiest problem all of us know. And it's kind of unbelievable that this is already the most difficult problem. For this question. I just don't get it, right? So it could be that the gain is 1, but it could also be that at some point we prove that 1/2 is really the best.
I will have one question, some clarification, maybe it's a little naive, but what you call algorithm is a composition of the observation process and the reconstruction process, and when you talk about randomized algorithm, randomization is allowed in both of them? Or in just one of them?
Randomization means you have a random variable, and a random variable is a function, right? Once you fix your small omega, it's exactly like this. But now you take the average over omega.
Yeah, but in both steps? You can do it in both steps? Or
yes, you can do it independently and whatever. As I said, the probability space does not play a role. Instead of taking one random element for the algorithm, kind of, you could take 1 omega for the one step and 1 omega for the other. It doesn't matter, right? There are general results that a kind of underlying probability space does not really play a role. You can formalize everything there.
All right, so let's have a coffee break, and for half an hour, we'll reconvene at 11:30, and thanks again for the